Hello and welcome back. So this will be the last week of classes where we are going to look at generative models, specifically generative adversarial networks. Okay, so we have usually seen data in the form of images, videos, again moving images, text, tables, numbers, etc. And these numbers are used as input for drawing some inference. Okay, and a variety of machine learning techniques are geared towards given an input, provide an output in the form of a classification or some regression value. Okay, so generative models are models that actually describe your data. Okay, so generative models try to model the distribution of the actual training data that is given to you. So that way you can say that generative models use probabilities to describe or characterize your data. So the data set D that is generally made available to you for training your deep neural networks can be seen as samples from a probability distribution P data, which is the true distribution of data. Okay, now this distribution is generally hard to get because you actually don't have access to all possible kinds of data corresponding to the problem that you are working on. So for instance, you are working on images of the brain, MR images of the brain. You would need access to pretty much all possible images of the brain, right? So every person in this planet, they're generally not available. So you have access to a small subset data of the data D, but then you see that data as being drawn from this probability distribution P data, which you would ideally construct using all the infinite number of samples, right? Typically, that's what you would look at. But then you have this subset of that, a small subset of that is made available to you for training, and you would actually, make an empirical distribution on P data that is the real distribution. Okay, so P data is the real distribution. You would make an empirical distribution from it using your training data set. Okay, so what is the idea behind generative model? Generative models try to approximate this P data given the training data D using neural networks. Using these neural networks, in general, you can say that using differentiable functions. Okay, but in this case, it's going to be deep neural networks. What is the idea behind this? Well, once you have this, the idea is that you can then draw samples from P data using the neural network. So either the neural network provides you with the parameters of the distribution itself that some models do, or it directly gives you samples from the distribution, which is what GANs does. Okay, so given, and it actually depends on one latent noise vector that you provide as input. We'll see that over the next two slides. But these are different kinds of generative models that you can have. So to summarize, you have the real probability distribution P data. This is generally not available to you, and you don't have access to all the data itself. So you only have access to your training data D, which is representative of the problem you are trying to solve. And what you are trying to do is to get a neural network to approximate this distribution P data. Okay, so what is the easiest thing to do? Easiest thing is to have parametric approximations to data distributions. They'll serve as good generative models. So for instance, if we can model our data as a Gaussian distribution, then we can just describe the data using the mean and standard deviation. And subsequently, we also know how to sample from this different distribution. So given this kind of Gaussian distribution, we would know how to sample it. Now the problem to be solved in such cases is to estimate the parameters of the distribution, which is again done by minimizing or maximizing an objective function. So what you would have is you will have a P model, okay, and then you have this P data. You actually don't have access to the real one, but you would have this P tilde data, which you would construct using the training data set D, and then you would try to minimize a distance metric between these two. Typically, the metric that you would minimize would be the KL divergence. Okay, it's called the Kullback-Leibler divergence, which is what is used in a lot of the estimation problems. Okay, so this is one way of doing it. Okay, and what you're going to look at is a particular technique which was published in 2014, which turned out to be a very popular way. Now it's also used very often to to provide generative models using deep learning. Okay, so how do you do this? How do you learn these generative models? What you have to do is find out a distance metric between the desired distribution and the training data distribution. So in a sense, you have your model, you call this P model, okay, or you can also call this P theta because theta are the parameters of the distribution. So for instance, if you are using Gaussian, it's parameterized by mu and sigma, which Bernoulli, you have the Bernoulli parameter, okay. And we want to estimate this p theta such that, there is some distance metric d between p theta and p theta, which is optimized, okay? Let's say maximized or minimized. In this case, minimized would be more like it, okay. But then, it's not so easy as it said, because, as the dimensionality of the problem increases, you are in trouble. So for instance, if you are trying to, let's say, approximate, find a generative model for images, so a 256 cross 256 image will have at least 10 raised to 4 to 10 raised to 5 parameters, okay, one for every pixel in it, okay. So that's a problem. So the number of so you will have an explosion in the number of parameters. You're trying to do this in a very straightforward brute force manner. So that's why this problem is generally very hard to do. Okay. So like I said, a typical medical image will have about 1 million voxels or more. And even if we quantize them to take values between 0 to 255, remember that a lot of the medical images can take a much more wider range of values. And given this, it means that every pixel can take 255 values. There are millions of pixels. So you can see that it gives rise to an exponentially large number of images. But the amount of data that you have to approximate this distribution is very limited. Okay. However, what is possible is that this image data has some structure to it, which can be extracted automatically using deep learning. And that's also another fact that we exploit when using generative models based on deep learning. Okay, so what have we seen so far in terms of, if you're going to use neural networks for analyzing medical images or in general images, right? So what we are seeing is we are looking at classifying pixels, classifying images. Now, these are typically known as discriminative models, because what you're trying to do is, what your output is basically is the probability of belonging to a certain class given the data. Now, this X is basically features extracted by the neural network, by the deep neural network. So that's typically what you are doing all the time when you train a network to either do semantic segmentation or image classification. So you're just training a discriminative model. So what it does is estimate class probabilities given the features P of I given X. And it also one way of saying that it models the boundary between different classes. Now what do generative models do? Generative models model probability distribution of the data corresponding to individual classes. So it's like you can think of it as modeling P of X comma Y. Okay, joint probability distributions can be modeled. So from there you can generate new data. So if you know Y, can we get X? Okay, completion, etc. So all of these are possible with generative models. So now in the recent past, the explosion in the sophistication of these models. So all those stuff you read about on social media, how images are generated, art is generated. So you input text, okay, you can think of, and then from there, from the text, images are generated. Okay, you input a cartoon and then pictures are generated. Faces are generated automatically. So all of those are generative models and they have a wide range of applications. So in the case of medical image analysis, what would you have? What did you see as an application? Medical image analysis, usually there is a paucity of data, especially labeled data. So in that case, if you can come up with synthetic data that can be used to train deep neural networks, so that they can be deployed everywhere. So the advantage of synthesizing data is that you can synthesize a wide variety of data. Maybe also try to model, how data varies from different centers or different scanners. Build that into this process and try to generate data that is realistic and can be trained, let's say, for classification, and then can be deployed in any hospital or center. Okay, so that's one of the one possible application here of generative models. Correct. So likewise, you can also try to simulate different types of pathologies. All of that is possible only using generative models of data. So in the context of vision and in general, if you think about any application, here are some applications, right? So for instance, the application that you would consider super resolution. So this is again in medical imaging, this is very useful. So how will you use it? So for instance, in order to get very high quality images, okay, from a scanner, typically let's say CT or MR scanner, the price of the hardware also goes up. Okay. So if you are able to set up a deep neural network or a generative model that can take low quality data as input and generate high quality, high resolution data, then you can actually make the scanners economical. So that's one very broad goal that can be for deep learning generative models in medical image analysis. Okay, the others are very useful in vision, colorization of grayscale images, predicting occlusions in images, wherein if you have damaged paintings, etc., you try to fill them in. Cartoon to image conversion, which you can use for designing, or even creating works of art. Okay, and of course there are always generative models of speech, text to speech, etc. So somebody speaks, you convert that to text. Somebody types it in and you convert that to speech, automatic speech generation, you can call it that. So in all of these, there is always an input. If you notice, for super resolution, you need to have a lower resolution image of the same object, etc. Okay, that's fine. So it is still generative because you can think of that lower resolution object as what they would refer to as a latent variable, as the hidden variable, which actually describes is a lower dimensional description of your real high dimensional data. Okay. So all of that is fine, but many of these are applications both in computer vision as well as in medical image analysis. Okay, so there are again multitude of applications. You just have to do a literature survey. You will see that. Okay, image translation. So if you give a semantic segmentation as input, it gives you a realistic scene. Once again, this can be used even for medical imaging. Of course, the problem with medical imaging data is that three-dimensional, inherently 3D, most of the CT and MR scans, and getting anatomically correct generation of images is a challenge. Okay, so there are multiple such applications. The recent past, I'm sure you've all seen in media or social media, huge photorealistic. So if you see this particular mosaic of images, all of them are fake, pretty much. They're not real people. Similarly, on the left, all these images are generated from deep learning models. Okay. Once again, they have a lot of applications, both for in media as well as computer vision. In the context of medical image analysis, like I already mentioned, it will be great if we can generate, let's say, anatomically correct 3D volumes so that we can use them for training. Of course, there's a further challenge. Annotation is also a challenge. There are variants of this to hopefully we can also have annotations automatically. The other application for GANs, for instance, generative models in general in the field of medical image analysis is in image guided surgery. Okay. So again, I'm just mentioning these applications. Okay. Of course, a lot of these are in the research stage. Find a lot of publications in this area. So image guided surgery is wherein most of the time your intra-operative imaging system is just a ultrasound imaging system, right? So during surgery, if you want to monitor your surgical tools, you usually have an ultrasound, or just plain camera sometimes. But your 3D high resolution image of the anatomy comes from MR or CT, which you took before the surgery. Okay. So now, if you want to align, we looked at image alignment or image registration. If you want to align the images that you take during surgery, either ultrasound mostly, with the images that you acquired prior to surgery, which is basically high resolution, then it will be nice if both of them are, the same type. So now you are going to have to do cross-modality image registration. It's generally a difficult problem. So it will be nice if you can convert the intraoperative images, basically your ultrasound images, into MR, so that the registration problem becomes much simpler. So for such applications also, you can use generative models. Of course, when I say that, these are again in the research stage, much difficult problems to solve also. Once again, here I am displaying this image translation wherein you have, based on a certain type of training, you can convert this image of a horse into that of a zebra. Okay. Generating speech from text. Okay, there's a WaveNet. You can look this up once again. We're not going to cover this in this class, but it's a very popular model. Similarly, generating sequences. A lot of the language models, you can consider them as generative, right? Because you just have to provide an input, starting sentence, and it completes the sentence. For instance, even image translation is generative, right? You provide as input in one language and the output comes in another language. Okay? All of these are basically generative model. Okay, so the model we'll be talking about in this class is the generative adversarial networks by Ian Goodfellow. It's a very popular work. When I say popular work, I mean in the context of a lot of citations. Of course, a lot of other publications have come off following this publication of GANs, generative adversarial networks, and we're going to look at this briefly because you're going to have a fairly long tutorial session on a neural network implementation, deep neural network implementation of this. Okay, so how does GANs work? How does it generate images? Okay, that's what we are going to look at in the following slides. Okay, so basically this particular generative model consists of two parts or two pieces. Should I say two functions, right? Which one is a generator, the other is a discriminator. Both of them can be neural networks. Okay. The generator and the discriminator, both are neural networks. Okay, so what does it do? So first, let's just look at the generator's work and then we'll look at the discriminator later. Okay. So the generator takes as input a latent space vector. So this latent space vector is often denoted as Z, and basically, and that Z is, you can also, and sometimes it's also referred to as noise, okay, vector, and that Z is most of the time, slightly lower dimensional than the data you are trying to generate, but ideally it should be the same size as the data you are trying to generate. Okay, so that's typically what is done. You will see that in the paper, the walkthrough that we will have in this week. Okay, so this Z is input, and the idea is it's called latent space, and to give you an understanding of what this might mean. So, for instance, if you think of face recognition, right? So, for face recognition, what would this latent vector be? It would be maybe a distance. So, one particular vector would be distance between the eyes, distance between the ears, width of your lips, the angle that your jaw makes with the vertical or the horizontal. Okay, the width of your temple, color of your hair coded in some form. So all of them in some form of numbers. That would help you reconstruct a face. Okay, all that data that you can think of visually, that will help you reconstruct a face accurately. So that would form Z. Okay, that's a good way of understanding what Z is. So if you sample Z, the idea is from Z you should be able to recreate samples of your distribution. Okay, so that's what this function does. This generator is a neural network. I call it a function. Okay, it's a differentiable function. It takes as input Z and outputs is G of Z. Now this G of Z is what you call a sample. It's a generated sample. Okay. Sample that's generated by the function G, which is in currently all of those are all of G's are just basically neural networks, right? So G of Z is the output from G. Okay. So these are generated samples, also referred to as generated fake samples. So these are fake samples. And then you have your training data, okay, your training data distribution. These are samples from the training data. You should have access to training data, by the way. You can't do this out of thin air. So you should have some access to training data, at least simulated, or some collected, some amount of it is required. So you take the samples of training data, okay, and you also by giving a bunch of latent space variables. So this latent space can be sampled from a uniform distribution, multidimensional uniform distribution. Okay, think of it as multidimensional uniform distribution, or you sample a bunch of numbers from there. So from uniform distribution, and for each one of your latent vector that you have sampled, you have an image generated, and that gives you a bunch of images, and you have samples from your training data. Okay, so what does this discriminator do? Discriminator is trained this way. So you have 50% of the samples which are input to the discriminator coming from the training data, 50% of the samples input to the discriminator coming from the fake data. Okay, so let's say 50 images from samples, 50 fake data, and the function of the discriminator is to classify them as 0 or 1, 0 corresponding to those generated by a generator, which you call fake samples, and 1 corresponding to the real data. So it's like two class problem. In this case, you assign it to one of either class. It's a real data or the fake data. Okay, fake data corresponds to one coming out from G. Real data is from the training set. Okay, so that's a discriminator. So the way this is set up is you now have these two functions, discriminator and generator, which are basically neural networks. And you have to train these neural networks to estimate the parameters of the neural network. So we will see how such training is done in the next few slides. So here's the loss function that is trained for training GANs. So the discriminator and generators have slightly different loss functions, but they vary in the sign. So the idea is the following: for the discriminator loss function, it's very similar to the binary cross entropy. Okay, I say very similar. I wouldn't say same. Because what happens is, all the positive samples, the 1 labels are drawn from the training data, all the 0 labels are drawn from the G of Z, or basically the ones that are generated by the samples. Okay, so by this is how you train the parameters of the theta of D or the parameters of the discriminator. The generator cost is exactly the opposite of it, right? Because you would want to fool the discriminator. The generator is actually trying to pass off the samples it generates as real samples or samples that come from the training distribution, from the training data. So its cost, you can say, is basically the opposite of what the discriminator is trying to do. Okay, so it will try to make the discriminator do more mistakes, in the sense it will classify fake data as real. So that's why you have the minus sign on it. Of course, when you are doing this term disappears, the expectation over the training data disappears, because you don't actually consider it, because you're only looking at the images that come from G of Z. So that's the generator cost. So when you have something set up like this, it's called the zero sum game or min max game. So basically you are maximizing over the parameters of one network and minimizing over the parameters of the other network, and this particular loss function. Okay, so we will look at it in slightly more detail over the next few slides. Okay, so let's look at the loss function for the discriminator first. So the labels, the true labels are 0, 1. Okay, that's the true labels. So which means that y is 0, meaning output of generator, which is fake, and 1 meaning from data from training data. This is training data sample, which means it's real. Okay, this is fake, this is real. Okay, so let's look at the case when the discriminator works properly, right? So when the discriminator works properly means d of x should be close to 1 when y corresponds to 1, that is training data, and d of x should be close to 0 when y corresponds to 0, correct? Because these are the class labels. And if you do that, then you will see that j takes the value close to 0. Okay. Now, when it misclassifies, what do I mean by misclassification? That when with a different color, so d of x outputs 0 when y is 1, that is, it misclassifies real as fake, and it misclassifies fake as real when actually y is 0. So you can plug these values back in here. So when d of x goes to 1, right, and in the sense d of g of z, right, you forget this one, you can forget this particular, when you're getting data from g of z, let's forget this. And if d of g of z turns out to be 1, this will go to minus infinity. So minus of minus infinity will be plus infinity. Similarly, when you're getting real data, this term won't be there, and that is data from the samples, training samples. So, and if you are misclassifying, then this will be 0, log of 0 will be minus infinity, so this minus here will make it plus infinity. So, the way to make the discriminator learn would be to minimize this loss function. So, you would minimize v of d, theta of d, theta of g. Okay. Once again, theta of g refers to the parameters of the generative model, which is another neural network. Theta of d refers to parameters of the discriminative model, which is another neural network. Okay, so what happened to the generator, right? So for the generator, it's slightly more tricky. So what we want to do is, if you look at it, we did it to be the negative of the discriminator's loss function. Now, in the discriminator's loss function, there was this term which had the expectation over the training data. We don't need that because for generator, it's only going to deal with samples from the generator. Okay, so the way you would do that is you would do the following optimization: maximize over the parameters of G the following minus log of okay. So what it would do? So if what it does is the following. Let's say when this generator does an excellent job, it generates a beautiful image, which is just like the images in the training distribution. Then d of g of z will become 1. Okay. So minus log of 1 minus 1 is 0. It will go to minus infinity. So minus of minus infinity, it will be tending towards plus infinity. Okay, so now what happens if the discriminator correctly classifies, correct? So which means that d of, if it correctly classifies, then d of g of z becomes 0, but then log 1 will go to 0. Okay, so this is basically your error signal that can be back propagated. Okay, so you would actually want signal from here when to improve the generator, correct? Because if the discriminator is able to correctly classify the output coming from the generator as fake, then that's not good for the generator, right? You'd like to use that signal to modify the parameters of the generator, but it turns out that in this heuristic it kind of becomes hard. So what actually in implementation is you would flip the labels, okay, so and then minimize the following loss. So the minimization of the parameters of G, you would do the following: minus log of d of g of z. Okay, so what happens here is that if you notice, when d misclassifies, in a sense it is correctly classifies g of z as belonging to fake, so it means it's 0. So then this function gets a maximum value, so plus to infinity. And if d of g of z, if d misclassifies it as true, then this output is 1, log of 1 is 0, so you get 0. Okay, that's the minimum value. So you want to minimize this loss function. Basically, you want to force the discriminator to make mistakes, right? In this case, the mistake is classifying the fake image as real. Okay. Now this is the same as inputting the image GZ, but with label equal to 1. Okay. Remember, we said the real image was label 1. That is, images from the distribution was label 1, and images from the generated by the generator was label 0. So this is what we do is you use this loss function, but we give the label as 1, and so that's how you would train the generator. So here is the brief look at the algorithm from the paper. So they actually train the the generator and the discriminator alternatively. So for instance, you would sample a mini batch of m noise samples from PG of Z. So this Z is just a vector of uniform distribution typically. And then you take the mini batch of m examples from the data and you update the discriminator. Okay. Similarly, sample mini batch of m noise samples from noise prior and you update the generator. Okay. So you can do this by by either finish the generator and discriminator, so on and so forth, and you can alternate. Okay. And that's how you would train these networks. Okay, so following this, we will look at so-called convolution-based generative adversarial networks, which will be part of the tutorial. Thank you.